Okay, again, good morning. I'm sorry for the error. So our topic for today is all about mechanism of plate tectonics. Well, okay, for a while. So before that, let's have first some questions that this questions must be answered at the end of the discussion. What is the importance of the discovery of the mechanisms that explains plate tectonics? Next, why there is a need to discuss a mechanism of how the plates are moving. Remember the discussion of Alfred Wegener, why he was questioned about his theory of continental drift. This is the one main reason why he was questioned, because he wasn't able to provide the mechanisms on how the plates moved, specifically why the plates move away from each other, because from the Pangaea itself it broke and move away from each other until this continents achieve its current position on the globe. Now that specifically question was not able to be answered by Sir Alfred Wegener, but through these mechanisms it explains a lot of things about how the plates in the continents moved on its current position. So let's have first some review. It is a layer composed of ferromagnesium silicates, mantle. It is the up and down motion of the particles due to temperature difference. Convection. He is the one who proposed mantle convection, Arthur Holmes. So I do hope you're taking down notes, because I might be giving 10 item questions about this topic. Now on this picture, remember again our discussion about continental. This is quite obvious. This one is a continental plate. This one is an oceanic cross or oceanic plate. As they collide, as you can see on the arrow, as they collide against each other, one plate subducts or moves down, and then the other plates just override atop of the other, leading to a formation of a trench. Trench is the deepest portion of the earth. The ocean floor is deep, but then again, due to a subducted part in here, it leads to a formation of a much deeper part of the ocean called as trench. Now, into this regard, it is not only the trench that is formed in here, it also forms volcanoes in here, because on this part, the interaction between the two creates a friction. Now, this friction releases heat. The heat melts up the rocks on this particular portion, and then the magma goes up because it is less dense than the surrounding rock. Now, the thing is, as an effect, it rises up, leading to a formation of volcanoes, mountain ranges on the upper crust. Why do great slabs of lithosphere, Earth's surface, moved? I'm sorry for the typo. Research shows the subduction slowly continues all the way to the core mantle boundary to a depth of 2,900 kilometers. So that subduction of oceanic floor or cool or less denser plate, on the case of oceanic crust, goes down continuously at a depth of 2,900 kilometers. At the same time, equal volumes of hot rock rises in the form of magma, as I've explained a while ago, beneath a spreading center. So that is actually the divergent boundary, forming a new lithosphere to replace that loss to subduction. Remember, on the subduction zone, materials are being pulled downwards. Now, if that is the case, some materials are being lost on the system, right? But no, it's not the case, because on the divergent boundary, the magma are rising up and leading to a formation of a new landform, new topographical feature. So it's just the same. If there is something lost on the system, or in the case of the subduction zone, there will be a new landform formed on the case or on the divergent boundary. The term convection refers to the upward and downward flow of fluid material in response to heating and cooling. So I do hope you do take down this question, because might be it will be given to my 10 to 15 item quiz. Next, on this picture, again, this is a Wadati-Benioff zone. Remember our discussion on Wadati-Benioff zone? This one is an area where earthquakes are more frequent on this area, because the activity of this plate, it depends on the activity of the plate. If it's so active, then there will be a frequent earthquake on this area. And as you can see, magma are formed in here, leading to the formation of volcanoes or sometimes series of mountains on the upper crust. The process of mantle convection continually steers the entire mantle as rock that is hotter than its surrounding rises towards Earth's surface, and old plates that are colder than their surrounding sinks into the mantle. Later, I have a figure. Single mantle convection cell may be thousands of kilometers across. In this way, the entire mantle lithosphere system circulates in great cells, carrying rock from the core mantle boundary to Earth's surface, and then back into the deepest mantle as shown on figure 6.9. So let's go to figure 6.9. So this one is a convection cell. Hello, good morning. So this is okay, to be continued. The process of mantle convection continually blank the entire mantle as rock that is hotter than its surroundings rises towards Earth's surface, and old plates that are colder than their surroundings sinks into the mantle. So this one is what do we referring as mantle convection, one of the mechanisms that explain how plate tectonics moved. So as you can see on this figure, you have a divergent boundary in here because two plates are moving away from each other. While on this region, as you can see, as one plates move away from each other, it bumps into this region or the continental area. As you can see, likewise on this area, it bumps or having a convergent boundary on this region, both on this region. And then as you can see, as always, the ocean floor goes down or sinks, and then the other one overrides atop of the other. Now this hot magma rising of the material coming from the magma, and then sinking of cold material coming from your oceanic floor, referring or also known as or on your subduction area or subduction zones, you have here a convection current. Hot material goes up, cold material sinks, you have a convection of your mantle. Or also known one of the most used mechanism, which is actually the mantle convection mechanism. Next. So this one is another figure. This is a very specific one. This is a spreading center. You have here the divergent boundary. This one is the ocean floor. And then as you can see on the oceanic crust, it forms mountains, or sometimes it would lead to a formation of a volcano. Or if it goes up to the ocean water, it can lead to a formation of an island such as Iceland. Iceland is formed through magma coming from deep part of the earth. And then you have here continental crust, another continental crust on this area. As we have a divergent area here or moving apart plates on this area, you have two colliding plates in this area. And then as an effect to that, one plate goes down. In here, one plate goes down and forms your subduction zone. And then the material goes back, goes back as a magma. And in here, you have the plates or the subducted plates will go back as a magma on this region, or becomes part of the magma. And then, as we do know, magma is less dense than the surrounding rocks. Thus, it will go up again, leading to a formation of volcanoes. Volcanoes in here. Sometimes it leads to a mountains. As you can see on this figure, you have a folded mountains. Again, remember our discussion on mountain ranges. Folded mountains are actually steep mountain, steep-sided mountain. Next, just as the soup on the stove rests on the hot burner and is heated by the hotter core, thus heat from the core is supplemented by additional heat generated by radioactivity within the mantle drives the entire mantle and lithosphere in huge cells of convecting rock. So as you can see, as we do cook, it's just the same mechanism. A tectonic plate is the upper portion of a convecting cell and thus glide over the asthenosphere as a result of convection. So just like when we are cooking, the first one that is being cooked is actually at the bottom, and then those heated material at the bottom then goes up, and then those cold materials at the bottom part goes down, and then the cycle continues, and then the whole as at the end point of that, the entire substances, including the liquid, the solid part or the meat, and then the veggies on that oven or the one that you are cooking is entirely being heated up. So it's just the same in the Earth's interior. Hot material goes up, cold material sinks. Two other processes shown in figure 6.14 may facilitate the movement of tectonic plates. Thus, heat from the blank supplemented by additional heat generated by radioactivity within the mantle drives the entire mantle and lithosphere in huge cells of convecting rock. Mantle plumes and hot spots. So these are the two remaining mechanisms by which our scientists could explain how the plates move. A mantle plume is a relatively small rising column of plastic rock, mantle rock that is hotter than the surrounding rock. Always remember this. If a substance is being heated up, it is actually lighter than its surrounding material or rocks per se. Now the thing is, if it is lighter, it will always go up. Okay, so just the same on the mantle. If it's too deep, then the tendency is that higher pressure on that area is met or meet rather, and then in accordance to that, there will be a high temperature on that area. So materials being compressed. Now, when the materials are being compressed, the temperature rises up. And then when that happens, the rocks are being heated up because of that temperature. Now, when that happens, you form a magma. Now, when there is a formation on that deep part of the mantle or of the mantle core boundary, it will go up and leads to the formation of a new island, new volcanoes, ridges on the ocean floor. Okay? Many plumes rise from great depths in the mantle. Magma forms directly above it at a hot spot in the mantle. A volcanic center just beneath the lithosphere that rises to erupt from volcanoes on Earth's surface. So, next. A mantle plume is a relatively small rising column of plastic mantle rock that is blank than the surrounding rock. So this one are the different mantle plumes that is rising from the core mantle boundary or from the deep part of the mantle or from the core per se, and then it rises up again as a magma. It is less dense than the surrounding rock. So this one, the bluish part, is not your magma, rather the yellow and then the orange or this red part. So they plume or they rises up on different parts of the earth. And as you can see, it can lead to a formation of a volcano or sometimes series of mountain ranges on different parts of the world. Now, if it continuously releases magma on this particular area, you call that one as a hot spot. Okay, again, if it continuously release magma on this particular area, because sometimes the mantle plume ceases or stops supplying magma. But in the case of a hot spot, that is the region wherein this mantle plume continuously supplies magma on this area, such as Hawaii. Hawaii is actually an island formed through a hot spot or a continuous release of magma on the same spot. Next. So this one is an example of hot spots, such as my example a while ago, which is Hawaii. So this is your hot plume material coming from the mantle or core mantle boundary. As it continuously releases magma, it leads to formation of a volcano right at the ocean part of the world. Now, if it reaches the topmost portion, you will just see a part of the mantle plume, just a part, because the entire part of the mantle plume can be observed at the bottom part of it. Okay, and most of its materials coming from the core mantle boundary. Why? Because it would be having a different material from the ones or from the rocks found on the oceanic crust, because the oceanic crust are actually been here before these mantle plumes are formed or released. Thus, it would have every time that there is a new release of magma in here, there will be a new material formed different from the ones formed from the oceanic crust. The Hawaiian island chain is an example of a volcanic center at a hotspot. It erupts in the middle of the Pacific tectonic plate because the plume originates rather deep in the mantle, far from any plate and below the level of lateral plate motion. So which means in a hot spot, its position never change. So it will continuously release magma on that particular area. Nevertheless, the case on Hawaii is that the plates on that particular area, which is actually Pacific plate, is actually an active plate. So it is not the hot spot which is actually moving, such as on this figure. It is not the hot spot which is actually moving or the magma which is moving. No, they are not the ones which is actually moving. They will just continuously be releasing. The magma will be continuously be released on the same spot. But in the case of the Pacific plate, as I've mentioned during volcanic, earthquake belt, and mountain belt, the Pacific plate is the most active plate. It will move. Thus, and the thing is that there will be a continuous release on that particular spot, but the thing is the Pacific plate moves. Thus, the effect is that there will be a new island form, because as if the original hotspot is on this area, so it will release a magma in here, leads to a formation of a volcano. But then again, the Pacific plate moves and it will form again a new volcano or an island in here. That process continues if the Pacific plate continue to move as well. Okay? So as you can see on the effect, as an effect to Hawaii, its original shape as an island is actually a lateral island. But as of today, its position is actually going to an L position. That is due, again, L position. Because that is due to the activity or the direction taken by the Pacific plate. The Hawaiian island chain is an example. I'm done with that. Mantle convection, again, let's go back, is a type of heat transfer usually observed among fluid molecule. Fluids expand and becomes less dense when heated. In effect, the less dense fluid rises away from the heat source. As it rises, it pulls cool fluid down to replace it. As a pulled fluid becomes heated, it also rises and pulls down more, that would be on the part of the subduction zone, creating a cycle that stops only when the heat is evenly distributed throughout the fluid. So when there is a continuous release of magma in here, and then there is a continuous downward pull of cool substances from the subduction area, specifically on the ocean floor, if the process continues and becomes a cycle, it ceases and becomes a convection current. Hot magma rises up, cold material from the subduction area, specifically on the ocean floor, goes down, and then the cycle continues. Then you have your mantle convection. Such as shown on the figure. This theory was proposed by Sir Arthur Holmes in 1929. Using Wegener's observations, Holmes suggested that as mantle became heated, its density decreases or it becomes lighter and eventually rises up. That is actually on the case of magma. Arthur Holmes stated that when the material cooled, again, going back, Arthur Holmes stated that when the material cooled, it would sink, exhibiting a circling behavior that is described like a conveyor belt. Next. According to Holmes, the pressure of heated magma broke the continents apart, forcing the pieces to drift in opposite direction. When the material sank, continents will be brought back together again. Tectonic plates are moved passively by convection currents in the mantle. Because when the material sank, they become part again of the mantle and recycled back as a magma. And then on the divergent boundary, as the magma goes up, they will become a new, it will form a new landform, a new land masses or topographical feature on that divergent area where the magma are being released. So mantle rocks near Earth's core become extremely hot, making them less dense than the cooler mantle rocks in the upper layers. Because as we go down to the Earth's interior, the materials are become hotter and hotter. So we would expect that the materials found, those on the core, is really hot than the ones found here on crust. In effect, the hot rock rises and relatively cooler rocks sink, creating a slow vertical currents within the mantle, which is referring to the convection current. So what happens during mantle convection? Again, may I reiterate on this, hot material goes up, creating or leading to breaking the crust on top of it, and then leading to a divergence, or it move apart the ones which is, or that area wherein the magma are being released. So it moved apart, leading to a formation of divergent boundary as per the explanation of Arthur Holmes. Now on this region that there is a divergence, on this particular area, on the sides, there is actually a collision on that area. It will bump eventually on that area wherein it is actually a continental by origin. And then when that happens, you have a convergence. One plate which is denser or cooler goes down, forming your subduction zone, and then those cold material will go back and be recycled back on the Earth's interior as a magma again. That is actually per the discussion of Sir Arthur Holmes. This convection current broke the plates or the crust into pieces and move with respect to one another. These convection currents in turn create convection cells circling within the mantle. So as shown on the past figures, that this mantle convections are actually found on different regions of the mantle. Whenever that there is hot magma rising and then cold material sinks on the subduction zone, then eventually there will be a formation of convection cell on that area. The convection currents push the magma up, forming new crust and exerting a lateral force on the plate, pushing it apart, leading to a formation of divergent boundary. Now, on this region, you have also a sea floor spreading. Again, on the divergent boundary, the oceans, because most often than not, magmas are actually our mantle plumes, hotspots such as in Hawaii, is actually formed or can be literally observed in a ocean floor. Now, if that happens in the ocean floor, the ocean expands. Okay? The ocean literally gets bigger. Okay? Now, with respect to the subduction zone, so it's as if you may figure it as, the earth is getting bigger because the ocean is expanding, as explained by this mantle convection. But no, it's not. Since we have a convection on the region of subduction zone, because there will be a collision. Now, in this collision, on the subduction zone, it will go back and becomes part of the Earth's interior. Now, the moment it happens, there will be no literally statements such as the Earth is expanding. No, it's not, because there is a region on the Earth referring to trenches, subduction zone, wherein the rocks or materials are being pulled towards the Earth's interior and be part again as a magma. Slab pool. This theory states that gravity and plates themselves are the ones responsible for the plate tectonics through subduction process. Diba? When we have subduction zone, the materials are being pulled down. No? Such as in gravity, all that has mass in Earth's surface are being pulled towards the Earth's center through gravity. So that is being explained by slab pool. Now, the one which is denser, such as on the case of oceanic crust, that one is much denser than the continental crust. It is the one being pulled or returned back to the Earth's interior and becomes part again of the Earth's interior as a magma. We are aware the subduction zone exists at the outer edges of the plates. Because at the center, you have a divergent zone. Now, on the side, you have subduction zone because there is a collision on both sides. Now, in these zones, rocks are older, hence they are cooler and denser compared to those located at the inner layers. The old rocks or slab also subduct and sink into the mantle below it due to gravitational forces because they are much denser. Now, these dense materials are being pulled towards the Earth's interior through the through the force of gravity. Such as this one, you have a divergence in here, magma are being released on this area, so you have moving a part of plates, so you have divergent. Now on this side, as always, it will meet a very stable continental crust or area. Now there will be a collision between the two. The one which is much denser, cooler, will be pulled through the force of gravity. So that's how simple it is. Slab pool, be understood by my students, specifically by you. I'm sorry for the typo, that is actually slab pull. As the slab is pulled down into the mantle, it drags the rest of the plate along with it, causing tectonic plate movement. So it's not only the rocks that are being pulled, or the slab of rocks that are being pulled, it is also, together with it, are the plates on that area. A very dense slab will sink faster than a less dense slab because of the gravitational pull, and it will exert greater force on the plate attached. The slab pull theory believes the mantle convection is not the cause of plate tectonics, but rather it is a product of subduction. So whenever there is a subduction, the subduction is powered by force of gravity. Now the thing is, there is an area that is being pulled back and becomes part of the Earth's interior again. Now, along with it, it is not only the rocks that are being pulled. Likewise, it pulls also the continents and plates, even huge plates along with it. What is the difference between slab pull and mantle convection? It's very easy. Slab pull is powered by gravity, whereas mantle convection is a natural process following hot material goes up and be released on the Earth's surface and leads to the formation of volcanoes and mountains or other topographical features. Likewise, cold material sinks and become on the part of the subduction zone and becomes part again of the Earth's interior as a magma. So, for you, which of the two best explains plate tectonics? Is it mantle convection or is it the slab pull? So, that's all for today. I hope you do learn a lot of things today. And I do hope you do take down notes because I will give 5 to 10 item questions after. So that's all for today. Goodbye and thank you, class.